In this video, I'll discuss the process of comparing the pH to the pKa. So there are some similarities and differences between these. They both provide a measure of acidity, however, what they're telling the acidity of is different. The pH measures the acidity of a solution, so a homogeneous mixture, so when you have two or more things that combine. However, the pKa measures the acidity of a compound, but more specifically is measuring the acidity of a proton within that compound. And a proton is simply a hydrogen ion, so a hydrogen that has a +1 charge because it's lost an electron. And so how easily that proton is removed or lost is what determines the pKa. And so acids and bases are concepts that were discussed in 1151. This video will focus primarily on acids, but if you recall from 1151, so I will just mention this real quickly, briefly. Acids, especially when we're looking at the Bronsted-Lowry definition, they're going to lose or donate a proton. Bases, they will gain or accept a proton. So we're either looking at the loss of that hydrogen ion or gaining the hydrogen ion. This video, again, I'm going to focus mostly on acids, which would lose. But regardless of whether you're dealing with an acid or a base, you have two different types. You have strong acids and bases, but you also have weak acids and bases. So for instance, if we're looking at hydrochloric acid. So if we're looking at hydrochloric acid and we decide to add that to water. If I'm adding that to water, what ends up happening is when this hydrochloric acid and the water combine to form that homogeneous mixture, that acid is going to completely dissociate. Dissociation is simply the process of splitting apart or breaking down to give ions. So that initial acid breaks down completely to give only ions. This represents what we call a strong electrolyte. Strong acids, strong bases, and even ionic compounds that are soluble in water are strong electrolytes. But of course, not every acid or base is going to represent a strong acid or strong base. For instance, if we have acetic acid. Acetic acid in water, it will break down to form ions. So we'll see CH3, COO minus. We'll also see the H plus, because anytime we're dealing with acids, they're going to release the proton or donate the proton. And so in this case, this particular acid, when it breaks down, it actually only breaks down partially. So it doesn't break down completely to only give ions, but instead you'll see a mixture. You'll see a mixture of the ions, but you'll also still have some of that original weak acid. This is what we call a weak electrolyte. Weak acids and weak bases are weak electrolytes. They partially dissociate or partially break down to give ions. And so this process is reversible because we can see where the weak acid breaks down to give the ions, but we can also see where those ions combine to go back to the original form. Weak electrolytes, the process is reversible. And so that's why you see the double arrow. It proceeds in both directions. Strong electrolytes, only one direction. Those ions are not going to come back together to give that original strong acid or strong base. But with the weak, they can. Eventually, the process in which the acid, that weak acid, is breaking down and those electrolytes or ions are coming back together, eventually both will occur at the same rate or the same speed. When this does happen, that represents what we call equilibrium. So equilibrium simply tells you that the speed of the forward reaction is the same as the speed of the reverse reaction. When that takes place, we can show an expression for that equilibrium. That expression, we can see it represented as K, or we can even see KEQ. The EQ just means equilibrium. At equilibrium, we can determine the concentration of products compared to the concentration of reactants to determine whether or not we have more products or more reactants at equilibrium. Because equilibrium just tells us that the speeds of the reactions are the same. It doesn't mean that the amounts or the concentrations are the same. And so when looking at equilibrium, only certain physical states are included. So you'll include certain physical states, the others you would exclude. If you have a pure solid or a pure liquid, those are excluded. The only physical states that you would include are going to be in the gas phase or the aqueous phase. So for instance, if we look back at our reaction involving the dissociation of acetic acid, we can look at the expression for that. Both products are in the aqueous phase because they're both dissolved in water. Anytime you see the bracket, that simply means concentration. I also have my weak acid. That was aqueous, so it will be included. So we have this expression. Because this particular equilibrium represents the process of an acid dissociating, you'll see this represented as Ka. That A just represents acid. This is known as the acid dissociation constant. So it's telling you how easily that acid dissociates. So again, how easily was that proton removed from that weak acid? Ka values for your weak acids, they're going to be less than 1. So you're going to be using scientific notation. For instance, the value of acetic acid at room temperature. This is a constant value. So the value of acetic acid at room temperature is approximately 1.8 times 10 to the minus 5. So of course this is the same thing as saying 0, 0, 0, 0, 1, 8. So 0.000018. That tells you how easily that acid is going to lose a proton. And so this is a constant value. As long as you're at room temperature, that is how that acid will dissociate. If your temperature changes, the value of Ka would also change. However, I mentioned that this video was going to be on pH and pKa. Right now we have the Ka. In order to calculate pKa of any weak acid, pKa is simply the negative log of the Ka. So whatever that acid dissociation constant value is, you're taking a negative log of that value. And so if we take the negative log of this 1.8 times 10 to the minus 5, and so you will need to use your calculator for this, you'll get roughly 4.76 or 4.8. This is the pKa of acetic acid. Again, at room temperature, this is the pKa for that acid. So pH. pH told us the measure of acidity of a solution. It's an acidic solution. pKa tells you how easily that compound can lose the proton. Your pKa values, so I'm going to go back up to where I wrote above. Your pKa values will range from approximately negative 10 to 60. The lower the pKa, the stronger the acid. pH ranges from 0 to 14. Again, the lower that value, but now in this case we're talking about pH, the stronger the acid. And so with this pKa of 4.76, even though it's a positive value, it's still very low compared to that pKa range. Strong acids, if we were able to determine their pKa's, they would be negative because they completely dissociate. There's nothing in the reactants. They all have values greater than 1. We're not going to see equilibrium. We'll only have products present. But weak acids, their value is going to be less than 1 because you're going to have a mixture. But whatever that pKa value is, the lower it is, the stronger that weak acid. And so, in order to determine the pH, so the pH of a solution, again, it's the measure of acidity of that solution. But the way you calculate pH is negative log of that proton concentration. Now, one thing to keep in mind, because we're talking about solutions, specifically aqueous solutions, whenever you have aqueous protons, because of how strong of an attraction that can form between that positively charged ion and that highly polar water molecule, you'll often see the proton written as H3O+. So whether you're seeing the proton or the polyatomic ion known as hydronium, they both represent an acid. So with your pH, you can see the equation negative log of the proton concentration, or you can see the negative log of the hydronium. They both mean the same thing. So let's go back. I'm going to go back to the equation with the acetic acid. This time, instead of showing water above the reaction arrow, I'm going to show it below. Because when an acid-base reaction takes place, you have your acid and you'll have your base. Now, water is a special compound. You'll hear it referred to as an amphoteric or an amphiprotic compound, which simply means that it can behave as an acid or a base. How it behaves depends on what it's in the presence of. If water is in the presence of an acid, then it will behave as a base. But you could also see reactions where water is in the presence of a base, and in that case, it's going to behave as an acid. In this case, we have water in the presence of acetic acid. So it's in the presence of an acid, therefore, it's going to act as a base. Recall the acids will lose a proton, the base will gain a proton. So the law of conservation of matter, when you learned about chemical reactions, you were told atoms are neither created nor destroyed. So this proton that is removed from the acid is essentially transferred to the base. So we're not losing anything, they're simply rearranging themselves. And so when the acid loses a proton, so if we look at this compound, you have two different places where hydrogen is located. You have hydrogen that's bonded to carbon. You have hydrogen that's bonded to oxygen. The hydrogen bonded to the oxygen forms a polar bond, whereas the hydrogen bonded to carbon is nonpolar. So those electrons are evenly spread out. But in that polar bond, because of the uneven distribution of electrons, that hydrogen is more willing to be removed. So it's going to be more acidic, more likely to be removed. And so, real quick, when you're trying to determine the formula that results from your acid losing a proton, think about it in two parts. Think about it in terms of the number of hydrogen. Also think about it in terms of the overall charges. So if you're starting with a compound that has the formula CH3COOH, and we're now saying we're losing a proton, so we're losing a hydrogen, We're simply removing one of the hydrogen. So we'll end up with CH3COO. But we also have to think about the overall charge. There's no positive or negative that I see for acetic acid, so that means that it's neutrally charged. So you're starting out with something that has a 0 charge. You're removing something that has a +1 charge, so a +1. You can show the plus if you need to. You don't have to, but if you take 0 minus a +1, you end up with -1. Put those two things together and you get the formula for the compound that results from that acid losing a proton. When the acid loses a proton, it forms what's called the conjugate base. A conjugate acid-base pair are compounds that differ by only one proton. We can do the same thing with water, but now instead of losing a proton, water gains the proton. So again, we can look at what happens in terms of the number of hydrogen, what happens in terms of the actual charge. We were starting out with H2O. We're adding a hydrogen. So instead of 2 hydrogen, we now have 3. We don't see an overall positive or negative, so we were starting out with something that was neutrally charged. We're now adding something that has a +1 charge. So 0 plus a +1 gives you a +1. Combine those things, and you'll end up with H3O plus. So when that water gained the proton, it formed what was called hydronium, which represents the conjugate acid. Again, your conjugate acid-base pair differ by only one proton. So the acid loses a proton to form the conjugate base. The base gains a proton to form the conjugate acid. So if we look at this, we have hydronium. Remember, hydronium was important because it determined the acidity of that solution. So I'm going to erase the rest of this at the bottom. Not only that, but we have this weak acid. We have a weak acid, which means it's a reversible process. So again, I can show my equilibrium expression. I would include both products because they're both in the aqueous phase. That physical state is included. I would only include one reactant, which is my weak acid, because water is in the liquid phase and it would be excluded. So this H3O plus, that concentration is what determines the pH of your solution. The Ka tells us how the acid dissociates. If we take the negative log of the Ka, then we'll get the pKa. So we can look at the relationship between these components to determine what happens when you compare the pH of a compound to the pKa of the pH of a solution to the pKa of the compound. And so let's think about what would happen if we have a very low pH. The lower your pH, the more acidic. So in other words, you have a higher concentration of the hydronium or the proton. So looking at our equation, you have your acid and your base on your reactant side, your conjugate base and your conjugate acid on your product side. But you have your hydronium on that product side. If you have more of the hydronium, Le Chatelier's principle. So I should have learned about that as well. Le Chatelier's principle told you that if a system is at equilibrium and a change takes place, that system is going to try to react in order to again achieve equilibrium. When I teach Le Chatelier's principle, I like to tell people to think about an actual seesaw. So if you're on a balanced seesaw, that will represent equilibrium. So I'll try to use this marker to represent that. So if I have a balanced seesaw, it's equilibrium. So just imagine this is even, a balanced seesaw. But if I'm saying that at a low pH, I have a higher concentration of hydronium, since hydronium is on my product side, your seesaw becomes unbalanced. Product side feels heavier. Reactant side feels lighter. In order to balance out that seesaw, so now the system is going to try to behave to again become back to a balanced state. Whichever side of your seesaw goes up, the reaction will shift in that direction. What that means is that it's going to form more of whatever is on that side. So because the reactant side in this unbalanced seesaw went up, the reaction is going to shift to the left, towards the reactants. What that means is that you're going to end up using this excess product that you have in order to form more of your reactant. So the reaction is going to end up balancing itself by shifting. When you use up reactants, it starts to feel starts to feel lighter. So the product side goes up. But then you're forming product, or in this case reactant. So that side feels feels heavier. Let me start that process over. I got a little tongue tied. So if our seesaw is unbalanced because we have a higher concentration of hydronium, so we have more on the reactant side. It feels heavier, so it gets weighed down, causing the reactant side to lift up. The reaction is going to shift and balance once again in equilibrium state. So it's going to try to balance itself back out. In order to do so, it's going to form more of whatever's in the direction of what lifted. So the reactant side is what lifted, what went up. So we're going to end up forming more of the reactants. In order to do that, we have to use up our products. And so as we're using or consuming those products, that side starts to feel lighter. But at the same time, we're using the products to form the original reactants. And so now the original reactant side starts to feel heavier, so it'll go down. So this side, product side, goes up while your reactant side goes down, and this occurs until, again, equilibrium is achieved. So thinking about that when we have a low pH. The low pH means we have more hydronium. So because we have more on the product side, the reaction shifts to form more of what's on your reactant side. So in that state, you're going to see more of the acid form. So you will see more, if we were just referring to this example, we would see more of the acetic acid. However, if the opposite were true, so let's say we have a high pH. The high pH is more basic. That's because we have less hydronium present. In that case, we have more of what represents the acid. So if I go back to my seesaw, so we're no longer at equilibrium. But now because I have less hydronium, hydronium is on my product side, that side now feels lighter. So that side goes up. My reactant side now feels heavier. Because the product side went up, the reaction is going to shift in that direction. So when it shifts in that direction, it's going to use up those reactants to form more products. So the reactant side goes up while the product side is going down at the same time until equilibrium is achieved. When that takes place, because we're forming more of the product, we're then going to see more of the product form, which is your conjugate base. So in other words, if your pH is high, so if it's more basic than the pKa, so if it's higher than the value of the pKa, you'll see more of the conjugate base form. But if the value of your pH is less than the value of the pKa, you're going to see more of the acidic form. So this doesn't just mean that the solution's pH has to be basic or has to be acidic, but what it means is that it has to be more basic or more acidic than the value of the pH. So for example, we could see this. Remember our acetic acid had a pKa of roughly 4.76. So we can see more of the conjugate base form even if we're at a pH of 6. A pH of 6 is still acidic, but it is more basic than the pKa. We can see more acidic form at a pH of, I could say, 2. Even though that is truly an acidic solution, we're comparing that pH of 2 to the pKa of that weak acid. And so again, if your pH, if that value is less than the value of the pKa, you're going to see more of the acid form. But if the value is greater than the pKa, you're going to see more of the basic form. If the value is equal, you're going to see an equal amount of the acid and the base. And so that is how you compare pH to pKa in order to determine whether or not you're going to see more of the acidic form or more of the basic form.